think that's it. Okay, so let me pull up. We'll go through we'll do some review. Maybe what I'll do.
Talk about the touchpad.
What's that?
The touchpad. Like, you guys really focus on
Nobody even selected that.
Wow. Wow.
Yeah, I don't actually have a module for that. And nobody put that down, did they? Well, I will say, how many of you tried to use a touchpad or use a touchpad in your project? Quite a few people. I mean, not the touch buttons, but the 4x4 plastic touchpad. Yeah. And how many found that to be surprisingly difficult? Yeah, it's really hard, right? And even if you get it working, it's still hard to get it doing a functional interface with a human being. Yeah, it's surprisingly difficult. It looks like it ought to be a piece of cake. It is if you use an Arduino. But that's because somebody already wrote the code. Okay. So let's see. Maybe what I'll do, maybe I'll start going over the modules and then I'll talk about, maybe I'll talk about the general things right now. Yeah, that's probably better. Okay, so I'll go over kind of the general questions and I'll start talking about the modules and I'll go through this. Okay, so like I say, I'll give you have one page, both sides of general questions, and then 10 questions on the module you selected. So for the general questions, I'll ask some questions about the Viva board. Okay, so I'll kind of give you some examples. What's that? I know. I'm not going to show you the test.
What's the problem with that? Sir, the screen's on. That's 0 to 1.
Okay, so let me ask you. So if you compare the KL25Z to the PIC, which one has a relocatable stack? No. The PIC's got a 16-level fixed hardware stack, whereas the KL25Z has a stack pointer, which you can load any address you want to, but hopefully you load one that's located somewhere in RAM. Typically you put it at one above the highest level of RAM. It decrements before you push the first value, and then it decrements into the top of RAM down. When you make variables, you put variables in at the bottom and fill RAM from the bottom up. So that's how the stack is supposed to work, and that's how it works in almost every single processor and operating system. And that's how compilers typically set it up. All right, which one, KL25Z or PIC 16 F1829, has a Harvard architecture?
Oh, that one.
PIC.
That's the PIC.
So, how many of you want to go ahead and just sign up for the fall? We're not really jumping on these answers. All right, you need to know this stuff. All right, Harvard architecture. PIC or KL25Z? How many think it's the PIC? How many think it's the KL25Z? You're wrong.
Jesus Christ.
It is the PIC. Okay? So remember, what is Harvard architecture? Separate data memory, separate program memory. 2 separate address buses, 2 separate data buses. And oh, by the way, all the data stuff and all the configuration registers are 8 bits. But the program stuff is all 14 bits wide, right? Which is one of the cool things about having a Harvard architecture. You can do that. Whereas, imagine having 14 bits instructions. You'd be throwing away, 2 bits out of every 2-byte instruction if you stored them in data memory. So it's kind of nice that you don't have to do that. Or stored them in flash that was byte oriented the same as the data. All right. How much RAM do you have on your PIC? Static RAM. About 1K. How much flash? How much flash? 8K, right? Okay. Yeah, you have 8K of flash. Who was it that did OLED displays and had 4 or 5 1K screens that you were writing initially? I know. Yeah, you guys did, right? Yeah. And you still had program, but you were trying to fill it up, though, right? Kind of ran out of memory, right? Yeah. So, but you do have 8K, okay? Which one of these processors has mostly 16-bit instructions? The KL25Z. But it does have roughly how many instructions does the KL20 have in its assembly language armamentarium? No, it's got 56. How about the PIC? How many instructions does the 8-bit PIC world have, roughly?
Oh, wait. I don't know.
It's about 50. I forget too. I don't even remember. But it's 48 or 50 or 52. It's in that range. All right. Which chip has built-in analog to digital conversion? No, they both do. Come on, guys. Jeez. This is terrible. Well, at least you can reuse your boards. So save them. All right. I was kind of hopeful that I wouldn't be down in the 20% DFW rate. All right. All right. So why do microprocessors have peripheral modules? What's the point? Why do we bother to put all this stuff on a single chip? Instead of, because we can buy all these peripheral modules in discrete standalone chips, right? Right? Why don't we do that?
So we don't have to put everything on a motherboard.
Well, your board would be a whole lot bigger, and you have a lot more screwing around, getting the parts soldered on, and traces connected. Yeah. But even more than that, if you buy the processor and then you buy 3 or 4 other chips, you're going to spend a lot more money. The processor is only $1, $1.25, $1, maybe 40 in small quantities. But if you buy an ADD converter, you're going to spend 75 cents for that maybe or more. If you buy timers, you're going to spend money on those. Yeah, I mean, there's a lot of reasons why microprocessors with a lot of modules on that chip, very powerful device for doing embedded design. It puts everything really on one chip. With rare exceptions, sometimes you need a few other things, like a display, or maybe a speaker, buzzer, maybe maybe an external temperature sensor. You do have one on the chip, so that's nice. Oh, by the way, the people doing the temperature module, make sure you also know about the internal temperature sensor on the chip. Okay. All right. So voltage regulator. So we have 2 voltage regulators on the chip. What kind of voltage regulators are they? Do you know? They're linear regulators, and they happen to be low dropouts for whatever good that is. Which means when the battery voltage drops below a certain point, the regulator stops. It just shuts off. It doesn't start to fail and deliver plenty voltages. It just shuts off, and that's desirable. What's one of the downsides of having the regulator on the board?
Just have to take up space.
Right.
Waste power.
Yeah, more power is wasted in your linear regulator powered with a 9-volt battery and running your chip at 3.3 volts. About double the energy is wasted in the regulator as the microprocessor uses, because it's a linear regulator. So whatever voltage is dropped across the regulator, that's the same currents flowing through there, so that's power. And you're dropping roughly 6 volts across the regulator and 3 volts across the micro. So it's almost double the energy wasted in the regulator than you're using in the micro when you're driving it with a 9-volt battery. A little better with a 5-volt. But yeah, that's a problem. So for a real battery operated device, you wouldn't want to do that. But we do that because we want to have a good stable voltage supply on your board. Probably if you're actually using it as a battery operated device, you would just let it operate at whatever the battery voltage was, and then when the chip started, when the chip got down to the brownout level, it would just shut off. And you could set that. You have two choices. I forget what they are. 1.8 volts is one of them. I don't know what the lower one is, or maybe that is the lower one. All right. What do you think are some factors that that cause us to? So in the old days, when we did embedded design, almost every embedded design was done with assembly language software. Now the trend is to do it in C. What are some factors that have changed that allow that? What's happened? Why are we all of a sudden writing everything in C for embedded design instead of assembly?
Compilers have gotten more advanced.
What?
Easier to understand.
Well, no, I mean that's a good reason, but what was that a change? Did it suddenly become easier to understand?
I guess it would just time a little easier.
No, I mean you're right, but that's not a good reason. That's not why it's changed. What has changed about our hardware or our development environments that has made this possible?
Speed of the processor.
Okay, so yeah, it does help if the processor is faster. So then it can, because our code is going to be a little more verbose with C. You can have a few more instructions to execute to get the same job done, basically, in most cases. Yeah, so that's probably true. Yeah.
Well, maybe because in assembler you need to be very, very specific. But now chips and those modern technologies, they allow us not to be as specific.
Yeah, that's part of it. But that's not really one of the things that's changed. What's changed about the hardware that has allowed us to develop in higher level languages? Or what's changed, not just the hardware, but in the whole ecosystem?
We've got better IDEs.
Okay, better IDEs, which means in the old days, there might not have even been a C compiler available. Although pretty early on there were, but initially there weren't. Initially all you had was assembler, so that was one reason. And also the IDEs do a better job of compiling. We have better compilers, they're more efficient. Yeah, so there's several things there. The IDEs have gotten better debugging that allows you to do source level even with a higher level language. Yeah, all the above, that's good. Okay, what else?
You have a lot more memory available
Yes,
now.
that's really the big change. Were you going to say that too?
Oh, I was going to ask you how do you think you were moving towards risk?
Well, not really, because the instruction set is almost identical to the very earliest chips. It has enhanced a little bit. What did they add? They actually added a few C-specific instructions, but pretty much and a few features like interrupt on change and some other things. But basically, the instruction set's not that different. But exactly, the real big change was in the old days you might have 128, not K, bytes of program memory. And when you have 128 bytes of program memory, and your printf routine takes 1K, really you can't take advantage of the power of a higher level language. Why bother? It's just not going to help you. You're going to blow through your memory instantly. And so you just wouldn't take the time, you wouldn't spend the effort to try and write the simple program you can put in say 128 bytes. You wouldn't need to write that in C because your program can't be that complicated. You only have 128 bytes. So more memory has really driven a lot of things. And one of the things it drives, of course, is you can use a higher level language now. Another thing it drives is your program can be a lot more fancy. You can do cool things that you couldn't do with fewer, with smaller program memories. So there are a lot of reasons why more memory has really driven embedded design in new ways. So that's probably one of the big changes, more memory. Yeah, and a lot of that came about because of the invention of flash. The old ROMs were just, in fact, the original microprocessors often had factory programmable ROM. So you couldn't even program it yourself. You had to develop your code, send it to the factory would burn it in when they manufactured the chip. And then as they moved on, they changed that. But the embedded controllers, that's how those initial ones. And then the next thing they did, they had memories that were ultraviolet erasable, so you could reprogram them, but you had to expose them to ultraviolet light to erase them. So there were things like that too. And then some that didn't have a window, they were one-time programmable, but you couldn't erase them because there was no window to shine the ultraviolet light on. All right, what happens when you have a pin on your chip that you set as an input, but you leave it completely disconnected? What is it going to read? You don't know. Yeah, it might read the same thing multiple times in a row, but you don't know what it's going to read because it could be 1 or 0. A floating input's a bad idea, and you don't know what it's going to read, and it actually could cause problems. Okay. Oh, one other thing. What about market forces? Do you think, as our chips have gotten bigger, I guess we still could have written our programs in assembler, but what about, kind of the market that we're, the market, the commercial world we live in now? How much, how many years do you have to roll out a product in this, in this market?
Less than a year.
Not very long, right? You got to roll them out fast, and if you miss a beat, somebody's probably going to beat you to the punch, and you may not get any market share at all. So the shortened design cycles also pushes to higher level languages because you can hopefully develop your programs a lot faster in higher level languages. Okay. How many bits of resolution do we get from our A to D converter if we get the maximum on our PIC, the 16F1829? How many bits does it give you?
5.
So that's D to A. 10, that's right. You get 10 bits of A to D. How many do you get on the KL25Z if you do the maximum, single-ended? 16. Yeah. All right, so it's a good idea. Now, if you're using your PIC and you're running at 10 bits of resolution and you ground the input to your A to D converter and you're using VCC and VSS and VCC as your voltage sources, what are you going to read once you do that conversion? What's the ADRESL and ADRSH? What value is going to be, say, right justified in those registers?
Can you repeat the question?
Oh, sure. Okay, so you have your A to D converter all set up for 10 bits, right justification, and you set your references at ground and VCC, and you ground the input pin to your A to D converter, whatever channel you selected. What are you going to read? That's right. What are you going to read if you set it to VDD? No. Who said? How many people said 1? That's a GPIO pin. Right. So you should take 2 laps around the building or something. All right. Yeah, this is an analog input. What's it going to read in ADRESL and ADRSH? The 2 result registers, each 8 bits, but we right justify it. So we got 8 bits in the lower register and 2 bits in the upper. What's our value if we set that input to VDD, to 3.3 volts or 5, whatever our chip's running at? 1023. That's right. Very good. Or something quite close to 1023. We would expect 1023, but we might get 1022. But actually, if you set it to VDD, you should get 1023. All right. Now, for some reason, that seems to be rocket science for some of the students. All right. But that's straightforward, right? Is there anybody that thinks about that and goes, "Gee, I don't understand it"? If so, raise your hand. Okay. What don't you understand about it?
So, I mean, 1023 is obviously some sort of multiple of 2s. I'm assuming you have a set of 1s.
It's 2 to the 10th.
2 to the 10th. Yeah, okay, so then you go 1 in every single bit.
That's
of
right.
Resolution. Okay.
That's right.
Cool.
Exactly.
That's it.
Yeah, you've maxed your number out.
I figured it because they would turn it on.
Right. Yeah, it should give you the maximum value, which is 10 ones.
Yeah.
Does everybody see that? Yeah. Every time I ask that question, that's a question that's missed a lot, and I like to ask that question. Okay, so that's a hint. So you should know that. Now what I might do is ask sort of the question that makes you think a little bit. What if you're running the chip at 5 volts and your input's 2.5 volts? what do you expect your A to D value to be read then? 512, exactly. Now, plus or minus a bit, I mean, and so there's always a range, because nothing's perfect. But yeah, roughly 512, maybe 510, 514, 511, 513, something. But it's going to be in that range, pretty close, right? That's straightforward, right? So that'd be a good question.
What is A to D?
Or what if I said, your chip's running at 5 volts and you put 1 volt in? What would you expect now? I can't do it. So it'd be 1/5 of 1024, whatever that is. Yeah, it should be 128. Right. Very good. It's a power 2.
That's not bad.
But a power 2 shouldn't be a 5th, right? Actually, that's an 8th, right?
Yeah, that's an 8.
Oh, 256.
No, that's 120 would be a quarter. No, 256 would be a quarter. 120 would be an 8th. You still haven't gotten a 5th.
Somewhere between that.
Yes, right. So you can figure that out in your head. I probably wouldn't ask that though, because you have to think too much. Okay. All right. So how many analog inputs are available on the PIC? Yeah, for the A to D converter, say. 12. How many touchpads can you have maximum on the PIC with the touch module? 4. That's how many you can have on your board. That's how many are on your board. But there's a potential to have as many as 12. Just exactly the same. All the analog things all track, and the comparator is the same, I think. All right. Although I never use a comparator on this board. Okay. If you want to use the A to D converter with C, are you going to right justify or left justify? Yeah, you right justify, and then you take the upper byte and shift it 8 and add it to the lower byte. Okay, when you do an A to D conversion, which bit do you start with? The higher order bit or the lower order bit? And you do it 1 bit at a time until you convert all 10 bits. High order, you go high to low. And that way, when you're done, you're plus or minus 1 least significant bit. The way and everybody, what do we call the actual electronic module on the chip that does the conversion? What do we call that module? Oh, what?
HD converter?
No.
80x1.
What's the method it uses?
Sampling.
What?
Sampling?
No.
No?
It's abbreviated this. It's abbreviated this.
Sequential approximation register.
Sequential approximation register. The SAR. Not the ZAR. The SAR. Okay. All right. Maybe that'll help you remember. What would be the advantage? Let's say you have a signal that you are going to input, and it varies from -1 to +1 volts, and you want to run it into your chip, and say your chip's running at 3.3 volts. Okay, what's wrong with this picture? What do you have to do? You're the engineer. How do you fix this? You what?
You have to do something to make sure the power.
You have to condition your signal. Yes. And how do you condition signals? There's a nice device. It's been around for a long time. Yes. An op-amp. And actually, what does op-amp stand for? Operational amplifier. And where did it get the name operational amplifier? Back in the day, these made up our computers. We had analog computers, and the analog computers multiplied, divided, subtracted, added, integrated, and took differentials. And so those were the operations. And the op-amp could do all those operations with the appropriate feedback resistors and capacitors. And so that's why they called them operational amplifiers, because they could do operations. Now we don't do them. We don't do analog computations anymore at all. But we do condition signals with the same amplifiers. And now the op-amps we have are just incredible pieces of technology. They go rail to rail. They have very little drift, they have very little offset, they have almost infinite input impedance, they have almost zero output impedance, and they have almost infinite gain. They are amazing devices. And so there are all sorts of circuits to let you DC shift this. So now it's 0 to 2 volts. And then if you want to tweak it up to 0 to 3.3, you just add a little bit of amplification. 0 shift, DC shift and slightly amplified. Or if you were plus 10 to minus 10, then you would attenuate it and DC shift it. But with the proper resistors on your op amp, with little voltage dividers on the input and feedback to generate amplification or attenuation, you can condition almost any signal with very little effort, and the op amp might only cost you a buck or two. In fact, some of these chips have them built in. It's really nice. This one, ours doesn't, but a number do. And you may need that for senior design, so keep that in mind. How many different simultaneous conversions? So how many different successive approximation modules are there on our chip? 1. We have 12 channels, but they go through an analog multiplexer. Only one can be connected at a time. So you can only do one simultaneous conversion. But you can scan up to 12 channels. And many of the chips, including the KL25Z, have what are called, they're more fancy A to D modules, and they allow you to have a scan order, to average signals, and to do all sorts of fancy things, all in the module, independent of the processor being involved. So it's very cool. And then interrupt when it's done, and here's your value. The other thing you can do, if you don't want to, let's say you have a signal that goes from 0 to 1 volt. So you don't have to necessarily condition this with an op amp, but what you might do in your A to D converter is you might use your fixed voltage reference set at 1.024 volts, and you might use that as your positive reference and ground as your negative reference, and that would give you better resolution across your range of interest. So that would actually give you more bits of resolution for your signal. Because you know, if you did the full thing, you would know above 1 volt, none of your signals are going to be between 1 and 3.3 volts. So you're wasting the bits of resolution that would cover that area. Okay. Okay. Let me shift out of this. We'll do a few more. Okay, so when you add touch sensing pads to a printed circuit board, is that an expensive thing to do, or is that like free? It's basically free. Yeah, it doesn't matter when they fabricate the board. They don't care if they make 20 touch sensing pads or none. It costs you the same. So that adds nothing to the cost of manufacturing the board. You might have to increase the surface area of your board, which could up your expense a little bit. But if you could fit them in the existing area, it costs you nothing, totally free. Why do we use the what's the purpose of connecting the master clear, setting for master clear, and then using RA0 and RA1? What does that get us with respect to, say, our PIC-KIT 3 or our SNAP?
Using that cheating.
Yeah, so it allows us to do debug. That's one thing. It also allows us to flash the chip with our debug header. Okay. Let's see the push button. When you push the button and it's set for reset mode, what are you actually doing? When you ground it. The master clear pin. That's right. And what is and what's connected to the master clear pin when you let go of the button? A 10K pull-up, right? All right. So what's the trend in operating voltages for microprocessors? Are we going up or down?
Down.
Yeah. What's one of the trade-offs as you go down? So less heat, that's one reason. Denser circuitry, so you get more transistors, more functionality. But what's one of the things you start to give up?
Resolution.
No, not so much that. speed. As those voltages go down, the rate at which your transistors flip slows down a little bit. And so on our chip, we have bypass capacitors on the board. Back in the day when we had to solder on all the parts, you would have had a better sense of how many caps you had to solder on. In this case, we actually have a lot more caps on this board than we did on the older board. We have 2 values of caps by the chip, and then we have 2 values of caps on all the voltage regulators. Why do we do that? What's the point of having? Well, first of all, what's the point of bypass capacitors? Yeah, so they filter out. So one of the features of CMOS technology is it really only draws current when it switches. But because the microprocessor is driven by a central clock, everything switches at the same time. So there's always big voltage surges inside the micro. And if you have a long supply line and no caps, then you're going to have some voltage swings. So that's a problem. But if there's noise in other circuits, it may get into your microprocessor through your VDD, and so you want to filter that out. And why do we use 2 different values of caps? Why not just 1 cap? What's the point of having 2 different values? I think we have maybe I forget what it is, maybe a 10, maybe a 0.01 or a 0.1. Why would we have 2 different values?
Different.
Yeah, they are a smaller value cap is a lot more adept at killing the fast spikes, and a bigger capacitor is a lot more adept at filling in the gaps that are caused by big current surges on the chip. So there's multiple reasons, but sometimes you'll even do 3 caps, and it's really 3 different bandpass filters essentially. Okay. All right. Which chip, KL25Z or PIC, has a 32-bit address bus? The KL25Z. Yeah, everything on the K is 32 bits. The address bus is 32 bits. The data bus is 32 bits. How big is the data bus on the PIC? Yeah, and how big is the address bus on the PIC? This is a great question. So, okay, how big is the address bus for the program memory? So it's actually just 15 bits, because that's what the program counter is. How big is the address bus on the data memory? Which also includes all the special function registers, your static RAM, all that. It is 12 bits. That's right. And when you have an instruction that references a static RAM address or a special function register, how many bits of that 12-bit address are included in the instruction itself, and how many bits are someplace else? It is 7. 7 are included in the instruction, and 5 are someplace else. Where is that someplace else? The bank select register, right? This is good. I don't think I've ever had a class that really had this down, and I think you guys understand this better than other classes have. So I might be tempted to ask that question. I've asked it a number of years ago, and it was a total bomb. But I think you guys probably get this. Is there anybody that's like really confused about that? Well, that the data memory, including special function registers and static RAM, everything is a 12-bit address. Everybody gets that? 5 of those bits are in the BSR and have to be set correctly, unless it's stuff that's replicated in every bank, in which case it doesn't matter what those 5 bits are. And the other 7 bits are embedded in the instruction. Everybody's got that? That's assuming you don't use indirect addressing, which we haven't used, and I'm going to leave that. I'm going to let that sleeping dog sleep. But it turns out when you write C code, you're only using indirect addressing. That's all C code uses. Everything's indirect. But and the KL25Z is almost all indirect addressing. But on the PIC, we're pretty much direct addressing things. Okay, let's see. When you do an embedded design development, let's say you're the boss. Okay, you got a team of 5 engineers. You're cranking out a project, and you've got several let's say you're making a toaster oven, okay? So you got somebody working on the human interface. They've got a little display that's going to read out the time and how dark it's going to be and stuff. And you've got maybe some touch buttons or maybe knobs. So what are some things you have to think about? So is it going to cost you more money to implement a touch panel, or is it going to be cheaper to put mechanical switches in? Touch is going to be cheaper because the switches cost more than the micro if you do 3 or 4 switches. Unless you put in super cheap ones, in which case your toaster's breaking and your boss is not going to be happy with you downstream. When you're planning this, let's say you've got somebody that's getting all the hardware put together and you've got a couple people working on the software. Are you going to include it so you can program your chips going out the door? Or are you going to plan on programming the chips early on in the development process and just soldering them on when they get the rest of the stuff done?
Early on. Put a toaster, right?
Well, so what do you think is going to be the longest pole in your tent? The hardware or the software? Almost always. I mean, just count on it. It's really rare when that's not true. So if you expect it and then it turns out to be the other way around, you'll be unpleasantly surprised. But you will have still put your money on the right horse. It just didn't work out this time, but it will eventually. Claim. Okay, so yeah, so what you normally want to do is you're going to go ahead and let them make the printed circuit boards, solder on the chips and everything up. Toaster's ready to go, just doesn't have the firmware programmed in. But you have it set up so you can just hook on a little device and program the firmware as they're going out the door. So you know it's the latest version, it's been fully debugged, and you're not waiting for the rest of the stuff to be done. I mean, you have to do prototypes and safety testing and stuff, but you're basically ready to go into production, and that last version of verified firmware is finally available, and so you're going to program that in out the door, basically. So yeah, you should plan like that. As you think about the cost, well, I don't know. So the microprocessor is not going to probably be the big cost of your product. I mean, you're going to spend a little bit of money on your printed circuit boards. They're not cheap. I mean, even making a lot of them, they'd still cost you money to manufacture those things. So when we bought the boards you guys soldered together, I bought 300 of them, and even at 300, they're still maybe 40 cents, 50 cents a piece, something like that. If I'd done 10,000, we probably could have gotten the cost down to 20 cents or something. But I mean, it still would have been somewhat expensive, right? They don't go to zero. Whereas the cost of microprocessor is only $1. So if you have a really complicated multi-layer board, you're going to spend more on your board than you will your micro. Okay, let's see. On the KO25Z, in order to use a GPIO pin, what are some of the steps you have to take? So what's the first step you have to do?
The gate stores, right?
Turn the clock on to the module, right? So if you're going to mess with port A, you have to turn the clock on to port A. If you're going to mess with an A to D, probably not going to write individual code for that, but you have to turn the clock on to the A to D, and so it goes. Every single thing, you have a system integration module, system clock gate control register, 4, 5, 6, and 7. And you have to set one bit somewhere in there, those 4 registers, to turn on the clock for every module and every port. And you don't necessarily want to turn them all on, but you do have to turn the ones on you're going to use. In fact, you probably don't want to turn them all on. Okay, let's see. What's the impact of using multiple modules on the cost of your design? Let's say you have a chip and you decide to use 4 or 5 modules on that chip. Is that going to, what's the impact of that on your product's cost?
I mean, you probably have more hardware. You probably have, hardware.
So you may not,
Modules already built in.
so if the modules are self-sufficient, you might not actually be adding any more hardware, right?
So,
Well, so there's a little more firmware development time.
space.
Yeah, that's going to add cost. But basically, the modules are already there on the chip. You're not even going to use them all. So if you decide to use a few others, you may increase the features of your product without really adding any significant cost, except maybe a little more firmware development time. Or maybe there's a display. But you know, adding an LED or something like that, that's practically free. Very low cost of that. You can buy 3,000 LEDs on a reel for you know $50, maybe less, maybe more too. But yeah, maybe 5,000 if they're 0603s.
Programs and LEDs.
Yeah, it's pretty amazing how cheap they actually are. Okay. Okay, so what are some of the debug features that your integrated development, the MPLAB X provided, or for that matter, the Code Warrior provided? So when you can single step through your program and you can see exactly where you are in the program, what do we call that? Source level debugging. Okay? Don't ever accept a project where you don't have source level debugging. Tell them to go find a better processor or a better manufacturing company or something. That would just be terrible. Okay, what do we call it when you can you can click on a line and then the code will stop at that point when it's executing every time it executes that line? Breakpoint. And what do we call it when you have a little window that displays you the value of a variable? Whenever it stops and you see the variable in that window, you can see its value. Watch window. Yeah, good. Can your debugger reach in and change values in special function registers and in static RAM? Yes, it can. It's very cool, right? Okay, that's all good. Let's see. So, do you still remember how to swap in assembly language preloaded values in X and Y with a scratch register Z? Does that burn in your brains? All right. Good. You never know. I might ask that. All right. Let's say we want to on the KL25Z. Let's say we want to toggle a bit. How would we do that? In some port A or whatever. So do we have a special register that lets us do that? Yes. So we have the port A underscore pin output pin toggle output register, the PTOR. So yeah. So how about clearing a bit? Same thing. Pin clear output register for that port. And wherever you set the bit, you affect that pin. On the PIC, we don't have that. So when we want to clear a bit, so let's see if we can do that. So let's say we want to on the PIC, we just have 8 bits, okay? Let's say we want to clear bit 5, okay? And so we'll do this in C. So normally we probably want to create a and we don't want to affect we don't want to affect any other bits. We don't want to change anything else, just bit 5, and we want to clear. Okay? How do we set this up to do that? We do a mask. Okay. So let's do the mask. So we'll do a 1 shifted 5 times to the left. So that puts the 1 in the bit 5 position. Now what else are we going to do with that mask?
Yeah, don't you need to clear?
We're going to clear. Right. So we're going to invert the mask with a bitwise inversion. And then we're going to, let's say it's port A or port C, say. We're going to equal, but we have to have some operator here. What's our operator? What? Ampersand. Yeah, we're going to AND it. We're going to AND it with port C. We'll AND port C and this bitwise inversion. And when we do that, we're going to essentially have 0, 0, sorry. We're essentially going to have 1, 1, 0, 1, 1, 1, 1, 1. So it's only going to affect this bit, and it will clear it when we AND it with port C. The other bits will be left alone. Okay? Sometimes it's better if you're going to do that, if it's an output, you might be better off doing the latch command. Because we're sort of assuming we're going to read what's on the port, but if some of these, but it turns out because we do read, modify, write, you can actually have unpredictable results unless you pay attention to that. So you always want to make sure you're reading what you think you're reading. And if you really want to read what's in the latches, then you have to read the latch. If you really want to read what's on the pin, then you have to read the port. Okay. Any questions about doing that mask? Is everybody good with that? Okay, we'll pick up on that on next Tuesday.